We're looking at some more trig identities today for when we have a sum and difference or when we have a double angle. And the first thing I like to point out is that you need these more complicated identities. Like somebody might first look at this and say, well, if I had sine of x plus y, could I just say sine x plus sine y? Would that work? Would I be allowed to do that? Well, let's look at an example. What if I had sine of pi over 2 plus pi over 2? What if somebody said, can I just distribute the sign maybe? Is that possible? And so what if we tried to do then sine of pi over 2 plus sine of pi over 2? Would that work? Would that be possible? Well, we know sine of pi over 2 is straight up. So straight up, your y coordinate is 1, so your sine is 1. So that would be 1 plus 1, that would be 2. So would that be the same thing? Well, there's an easier way to figure this out here. Pi over 2 plus pi over 2, half of pi plus half of pi. That's the same thing as sine of pi, right? Well, sine of pi is over to the left. If you're over to the left, your y coordinate is 0. Sine of pi is 0. 0 is definitely not the same thing as 2, so this definitely does not work. There's no such thing as distributing a sign. Sign's not a number, it's a function. Um, you can't just say sine of x plus y is sine of x plus sine of y. You need these more complicated identities. Okay? And similarly here, sine of 2x, you can't just like bring the 2 out. Sine of 2x is not the same thing as 2 sine x. There's this more complicated identity. And this one actually comes from the sum or difference identity. So take a look at this here. Let's say we were trying to figure out sine of 2x and we didn't know what it was. Can you figure out how you could use that sum identity there? It has to do with what 2x actually means. So of course 2x is 2 times x, but what does multiplication actually mean? What does 2x actually equal? What is 2 times x? What does multiplication mean? Multiplication is actually repeated addition. 2x is the same thing as x plus x. So if I wanted to find sine of 2x, I could find sine of x plus x. And so then we could use this identity right here. Just instead of an x and a y, we'd have both of them being x's, right? Now, one trick for me that helps me remember these right here, what I remember is that for sine, the sign is the same. So sine with a G means positive or negative, right? So for sine, the sign, the positive or negative is the same. If you started with plus, you end up with plus. If you start with minus, you end up with minus. Okay? And then for cosine, that means it's different. So only for sine, the sign is the same. For cosine, it's different. But then I remember there's always kind of something that's the same. So for cosine, the sign is different, the plus or minus is different, but same functions go together. So sine is different, but the plus or minus is different, but the trig functions go together. Cosine goes with cosine. All right, so different plus or minus, but same functions together. Whereas with sine, the sign is the same, the plus or minus is the same, but different functions go with each other. Sine goes with cosine, cosine goes with sine. Okay, so for here I would say, okay, sine of x plus x, so sine, the sign is the same, so since it started with plus, I'm going to have a plus here. And then the first one is always whatever this function is of the first angle. So I'm going to start with sine of x. And then because the sign was the same, the functions are going to be mixed. If I have sine here, I'm going to have cosine there. And now this is going to be my second angle, but here again, that's just x. And then over here, now they're going to switch. So if I had sine here, now I'm going to have cosine of that angle. If I had cosine there, now I'm going to have sine of that angle. All right. Well, let's take a look at what we've got here. So sine x, cosine x, cosine x, sine x. Well, multiplication is commutative, right? This cosine x, sine x, that's the same thing as sine x, cosine x. So really, these two are exactly the same. I've got something plus that something again. I've got two of that something. If you have two of them, you have two of them. Just like x plus x, you've got two x's, you've got two x's. Something plus itself is two of that something. That's the situation that we have right here, since this cosine sine is sine times cosine. So I've got 2 sine x cosine x, okay? And similarly, this cosine 2x formula would come from using the sum identity. I think that's actually going to be one of your homework problems, is to use this idea of replace 2x with x plus x and use this identity. Right? But other than maybe where these come from, most of these are pretty kind of straightforward. Just plug and chug with these new formulas that you've got here. So let's say we want to simplify cosine of pi over 2 minus theta. Okay, so I remember sine, the sign is the same, so that means cosine is different. So cosine, if I start with a minus, now I'm going to have a plus in the middle. Okay, so I'm going to start with this function of this angle. So I'm going to start with cosine pi over 2. And then since the sign, the plus or minus, was different, that means I'm going to have same functions together. So cosine with cosine. And I'm going to use the second angle. All right, and then for the second part here, just the trig functions switch. So instead of cosine, I'm going to have sine of pi over 2. Instead of cosine, I'm going to have sine of theta. All right, now we have to figure out what the heck we're going to do with this. Okay, at first glance, for some people, that just looks like a bunch of Greek letters. It's kind of like, what do we do from there? The thing is, you've got to realize that some of those Greek letters are different from others. So theta is a Greek letter, but that's a variable, right? Theta could be x. We don't know what this is. This is an unknown. Pi is a Greek letter, but it's not an unknown. It's not a variable, right? Pi, this, and in fact pi over 2, this is an angle right here. These are known quantities. What I'm going to do is I'm going to figure out what is cosine of pi over 2 and what is sine of pi over 2. Those are numbers. So pi over 2, of course, is straight up on the unit circle. So the y coordinate, or the xy coordinates, would be 0, 1. And so that means cosine of pi over 2 would be 0. So I'm going to have 0 times cosine of theta. And then sine of pi over 2 would be the y coordinate. So I'm going to have 1 times sine of theta. And so then that's just 0. And then 1 times something doesn't do anything. This is just sine of theta. Simplifies down very nicely. Okay. So that's our answer right there. Again, make sure you keep straight what's an angle versus just what's a variable, what's an unknown, what's a number versus just what's a function expression you can't do anything with. Okay, and then I just want to kind of make a note here. This is actually called a co-function identity, and in some classes they would make you memorize a bunch of these kinds of identities. Because this kind of makes sense if you think about right triangles. So this is the same thing as saying, if we thought about it in degrees, cosine of 90 degrees minus theta. Okay? And so we're saying that cosine of 90 degrees minus theta is the same thing as sine of theta. So what's happening here is kind of like what we noticed with pi over 3 and pi over 6, 30 degrees and 60 degrees. What we noticed, or hopefully you might have noticed by now, the sine of 30 degrees is the same thing as cosine of 60 degrees. The sine of pi over 6 is the same thing as cosine of pi over 3. Think about this in a triangle. If you look at a right triangle here, if we've got 30 degrees here and 60 degrees there, this was 1, this was root 3, this was 2. So if we made 30 degrees be theta, if we're looking at 30 degrees, if 30 degrees is the theta, our angle we're focused on, then 1 is the opposite and 2 is the hypotenuse. And so if we do sine of 30 degrees, we're going to get the 1/2 here. If we do cosine, we're going to do root 3 over 2. If we're focused on 30 degrees, this is opposite, this is adjacent. Well, if we look at the 60 degrees, it just flip-flops the opposite and adjacent, right? If you look at 60 degrees, this is the opposite, and that's the adjacent now. If we switch which one of these angles we're looking at, then the opposite and the adjacent, which one's labeled opposite, which one's adjacent, is going to flip-flop. And so, and of course, these, since they're in a right triangle, we've got this is 90 degrees. These other two angles, well, in a right triangle, will always add up to 90 degrees. So this angle is 90 degrees minus that angle. So that's kind of the logic of why, if you thought about right triangles, you could see that you're going to have a bunch of identities like this. Um, Cosine of 90 degrees minus theta is sine of theta. Cotangent of 90 degrees minus theta would be tangent of theta. There's a lot of what they call cofunction identities with this kind of thinking, this kind of idea. Okay. In this class, though, you don't really need to memorize those. We don't really think those are that important, but just wanted to mention that. All right. Why don't you go ahead and try this next example here? It'll be a little more complicated than the one we did because there's two separate things here. So you might get stuck at one point, but see how far you can get. See if you can figure this one out. At least try to write out, using the sum or difference identities here. Try to write it out. Try to start simplifying that as much as you can. See how far you can get. Go ahead and give this problem a try. Okay. So this one actually just equals cosine of theta. It simplifies quite a lot. So the idea is when we write this out here, when we write both of these out, we get a lot of things that look the same. So both of them have a sine pi over 6 cosine theta, sine pi over 6 cosine theta. So we can use that idea again of if you've got two of something, you've got two of them. This is like x plus x equals 2x. And then over here, we've got cosine pi over 6 sine theta, and then here we have minus cosine pi over 6 sine theta. So these actually canceled out. This is like x minus x cancels out. Same thing, but one positive, one negative. They cancel each other out. And then again, pi over 6. The ones with pi have to stand out. Those are actually numbers. You can figure out sine of pi over 6 is a half. 2 times a half is 1. And we just get cosine theta. All right. So this is our sum and difference identities we've been using. Let's take a look now at the double angle identities, trying to use that. Now we'll go ahead and solve some equations with those. Right. And so the first thing when you look at these, it just kind of has to click to you like, oh, hey, there's an identity for that. There's a formula for that. Like they used to say, there's an app for that. So sine of 2 theta, as soon as you see that, you think, oh, there's an identity for that. And let's just replace it with what it was. Okay. So we just kind of need to know that sine of 2x equals 2 sine x cosine x. We just need to know that. And so we replace this with 2 sine theta cosine theta plus cosine theta equals 0. And then from there, we just solve it. So we've got equal to 0 and factor was our most powerful equation solving tool. So we can factor out this cosine theta. We'll have 2 sine theta plus 1 left there. Then we've got our 0 product property. Cosine theta equals 0. And then if I have 2x plus 1 equals 0, I'll have x equals negative a half would be the solution here. So subtract the 1, divide by the 2, we get negative a half. So then we need to do some unit circle thinking here. So if we want the cosine to be 0, we want the x coordinate to be 0. That means we didn't go anywhere sideways. It means we're on the y-axis. So we're looking for those angles there. So we're thinking pi over 2. And then pi over 2 is not the only angle that's straight up, right? There's an infinite number of angles that are straight up, a whole bunch of coterminal angles that are straight up. That's why sometimes we put plus 2 pi n over here. You would want to be thinking, should I put the plus 2 pi n? Do I need to put all the solutions by putting plus 2 pi n? And the answer here would be no. We said over 0 to 2 pi. We restricted you. We can't give all the solutions, just the ones between 0 and 2 pi. We can't add or subtract full circles. So we're just going to put the pi over 2 and 3 pi over 2. When we say over 0 to 2 pi, that means no plus 2 pi n. All right, then over here, so if we want sine to be a half, we know it's got to be some sort of pi over 6. We know the reference angle has to be pi over 6, thinking about a y coordinate of 1/2. And then because sine is negative, ASTC, again, where I'm sure we're probably over 100 times already now in this class. Thinking about ASTC. We'll see if we can get to 1,000 by the time we're done. Using this a whole lot. So sine being negative, that's going to be the third and fourth quadrants. So we need to think about having a pi/6 reference angle in those quadrants. If that takes you a minute, that's okay. You can always pause the video for a second if you want to think about that. But that'll be 7 pi/6 and 11 pi/6. And so all four of these angles are our answers to the problem. So we just need to recognize that we have an identity for this term right here. Plug that in, and then from there, it's exactly what we were doing the past couple days. So why don't you go ahead and try this second one here. You're just solving over 0 to 2 pi. Now we'll have a cosine 2x in there. And one thing to notice for cosine 2x, there were a few different options here. So it's kind of up to you whether you always want to use this first one. You could just always use this first one, and then sometimes you'd need to use some Pythagorean identities. Or you could say, hey, I'm going to know all three of these. If you know all three of these, then you want to pick which one is going to be most useful in each circumstance. So it's up to you whether you're going to just know the first one, always use that, and then maybe use some Pythag, or whether you're going to know all three and pick which one works the best. Right? But you've got to at least use one of those right now. And then once you've used that, you should be able to solve that equation pretty easily. Go ahead and give that a try. All right, so yeah, I've got in parentheses here, so you might have skipped these first couple steps here. If you knew all three of those identities, then you would say, well, I've got a sine term here, so I would pick the one that only has sine in it. That would be the one that would be most useful. And so if you knew all three of those options, you could go right from what we started with to this third step right here. If you were only going to know the first one, if you only knew cosine squared minus sine squared, well, then you would have to use that. And then you would be using a Pythagorean. You would say, well, having both cosine and sine here is going to be a problem. This sign doesn't have a squared on it, so there's no way this sign is going anywhere. Remember, Pythagoreans, you can only use if there's a squared on it. Never, ever use Pythagorean if there's no squared. So that sign's not going anywhere. So let's try to get rid of the cosine, replace it with something that has sine in it. So we would use sine squared plus cosine squared is 1. Figure out what cosine squared equals. Replace cosine squared with that 1 minus sine squared. And then we end up getting a quadratic in disguise. I moved everything around so that my squared term was positive. That makes it easier for me to factor. Might not bother you, but I like to have my squared term positive. And again, it's up to you whether you want to just factor with the sine function right away. When you're looking at this, you could say to get 2 sine squared, I need 2 sine times sine. To get 1, you need 1 times 1, and then just make the factoring work. You don't have to do this u substitution if you don't feel like you need it. But if it helps you, then definitely do this u substitution. But either way, you've got a quadratic here, and then we can solve that pretty easily. And again, we don't put the plus 2 pi in because we were just solving over 0 to 2 pi. So we just want these angles right here. But we do have to give more than just the first one, right? In the previous section, we asked you for just the smallest answer, just the first answer. We're not asking for that. We want all the ones over 0 to 2 pi. So we do need both the third and the fourth quadrant here.